In this video, we take a look at chapter 3.3, properties of determinants. So our learning objective for this video is to find the determinant of a matrix product and the determinant of a scalar multiple of a matrix. In the next video, we will cover the learning objectives to find the determinant of an inverse matrix and recognize equivalent conditions for a non-singular matrix. And we will find the determinant of the transpose of a matrix. Let's start with theorem 3.5. This is about the determinant of a matrix product. So theorem 3.5 says if A and B are square matrices of the same order, then the determinant of the product of A and B is the same thing as the determinant of A multiplied by the determinant of B. So let's start on our proof. So to begin, we're going to let E be an elementary matrix. Remember, elementary matrix does row operations when we multiply it by the matrix. So some matrix EB is going to be the matrix obtained by applying the corresponding row operations to B. So by theorem 3.3 from the last section, we know there's three possibilities that correspond with parts A, B, and C of theorem 3.3. So our determinant EB could equal negative determinant B if that elementary matrix E is exchanging two rows. If our elementary matrix E is adding a multiple of one row to another, that's not going to change the determinant. That was part B of theorem 3.3. And if the elementary matrix is multiplying a row by a non-zero constant C, then that determinant is going to become C times determinant of B. So depending on the row operations corresponding with our elementary matrix E, then we have three possible outcomes that can happen to the determinant of the product. We can get a negative determinant, we can have the determinant unchanged, and we can have a constant C multiplied by the determinant. We also know from theorem 3.3 that the determinant of E is the same thing as the determinant of E times the identity. And that's because we know the identity doesn't change matrix E. And so if the identity is by itself, its determinant is just one, right? The product of the diagonals. And so if we multiply elementary matrix E by the identity, there's three possibilities. If the elementary matrix is exchanging two rows of the identity matrix, then we're going to get a negative one, because that's like negative times the determinant of I. So that would be negative one, since the determinant of the identity matrix I is one. The second possibility is that we're adding a multiple of one row to another, so we know that doesn't change the determinant. So the determinant of EI would be 1 in that case. And the third possibility is that we could multiply by a row by a non-zero constant C with this elementary matrix E. And so then our determinant would be C times the determinant of I. The determinant of I is 1, so that's just C times 1, or C. So we've shown the determinant of EB is just equal to the determinant of E times the determinant of B. So we can generalize this by induction to conclude that if we have K elementary matrices here multiplied by B and take the determinant, that's the same as taking the determinant of each of these elementary matrices and multiplying that by the determinant of B. And that's where the E sub i's are the elementary matrices, and our indices here go from 1 to K. So there's K elementary matrices here. If A is non-singular, then if we go back to theorem 2.14 from chapter 2, we remember that we can write this as the product A equals all the elementary matrices multiplied. So then we've just replaced essentially this product here with matrix A. So we've proven that AB, a product's determinant, is the same as the determinant of A times the determinant of B here. Okay, so remember that saying that a matrix is non-singular means that it's invertible. So we need to now think about the other case. What if the matrix is singular or we can't invert it? So if A is a singular matrix, then A is row equivalent to a matrix with an entire row of zeros, right? Because we can't find the inverse of that matrix, and we know A is a square matrix. So the example they give is a reduced row echelon form. So from theorem 3.4, we know the determinant of a matrix with an entire row of zeros is 0. Moreover, because A is singular, it follows that the product AB must be singular, right? If you multiply A times B, you're not going to be able to have a determinant, or it's not going to be invertible. And you could think about that by contradiction. So if the product AB were non-singular, meaning you could invert it, then A times, in brackets, B multiplied by AB product inverse equals the identity would show that A is not singular, right? If you could have an inverse of that product, because then A inverse would equal B times AB inverse, so A would be invertible, so it would not be singular. So by contradiction, it must be that AB is singular. So therefore, our determinant of the product AB is 0, and that equals the determinant of A times the determinant of B, because we know determinant of A is 0. So this is a 0 times determinant B, which is going to equal to 0. When we do a proof by contradiction, we're saying P implies Q. That's equivalent to saying, well, if not Q is true, then that implies not P. So sometimes we write this with logic like P implies Q is the same as saying not Q implies not P. This is the not sign in logic. All right, so let's do an example here. Let's verify that the determinant of matrix A times the determinant of matrix B is the same thing as the determinant of the product AB. So we've got a lot of calculations to do here. So let's start with the determinant of A. So the determinant of A is going to be the determinant of this matrix here. I'm just copying down the values from matrix A. And now I'm going to do some row operations on A. So you can check out row operations you could either do reduced row echelon form, or you could look at, well, what can we do up here to get all ones, or one in the leading position of A. So by row operations, we can get to here, 1, 1, 1, 0. The second row doesn't change. The third row doesn't change. And of course, you could do the determinant in SIMPy as well. I'm just working this by hand. All right, so you see here, we were able to get here by taking, looks like we subtracted row 3 to get to this one. And then we can make use of the fact that they're all ones here and set up the expanded values times the cofactors. So 1, taking this first one here, I'm going to get 0, 1, 1, 1, 2, 3, 1, and 1, 2, 3. Okay, I'm going to take this one instead for ease of calculations. So we'll leave this here because there's a 0 in this row as well. All right, so this is going to give us the remaining values here. Oh, you know what? I'm going to take, looking at my notes, I'm going to take this one first. So then I have 1, 1, 1, 2, 3, 1, and 1, 2, 3, because I've eliminated all the other values in the rows and the columns. This is my choice here, not this one. Because see how all the other values in this column are zeros? So that means I only have to do one determinant here when I expand the cofactors. If I'd chosen one of these other 1 values, I would have had more determinants to expand. So everything else is going to just be 0 times their cofactors from this column. Does that make some sense? So if I choose the 0 here. Well, 0 times the cofactor zeroes it out. Same with these other two positions. So my smart move was to choose the one that is in row 2, position 4. Okay, so here's my determinant to solve. And then I can use reduced row echelon form to make this determinant a bit easier. So get a 1, 1, 1, 0, 1, negative 1, 0, 1, 2. And then if we choose this one here, then our determinant is just 2 minus negative 1 or 3. So determinant of A is 3. All right, let's do the same thing for the determinant of B. And again, you can do this in SIMPy. I just want to show how we can use the row properties that we learned in the last section to make our calculations a bit easier here. So matrix B is 1, 0, negative 1, 1, 2, 1, 0, 2, 1, 1, negative 1, 0, and 3, 2, 1, 0. So we can do reduced row echelon form here. Well, we'll just do some row reduction on row 2. So we won't go all the way to REF. Okay, so you can see then now we've just got 2 spots to do here. So we can do, actually here's a good choice. We can choose this one. So by row reducing, or by just reducing row 2, by multiplying it by, it looks like we multiplied it by 2 times, or negative 2 times row 1, I think it looks like. Then no, it was row 3 maybe. So then we end up with just a 1 here. So then our cofactor matrix is going to be this here. And this 1 is in the first row, 4th position. So that's going to be a negative 1 to the 5th times the determinant of 0, 1, 2, 1, 1, negative 1, 3, 2, 1. All right, so that gives us negative of this determinant, 0, 1, 2, 1, 1, negative 1, 3, 2, 1. And so that is, we can do some row reduction there. Let's cancel out the 0 here. Turn the 3 in row 3 position 1 to a 0. We do 0, 1, 2. Second row stays the same. And then multiplying row 2 by 3 and adding that to row 3. Or subtracting it from row 3, we get 0, negative 1, and a 4. And so then we can use this one here, and our matrix becomes this here. So we have negative 1, 2, negative 1, 4. So this is going to be, oh, and our 1 is in position row 2, column 1, so that makes this even, so this becomes a plus. So then we get 4 minus negative 2. So the determinant of B is 6. All right, so determinant B multiplied by determinant A. Or actually, I should say it in the other order, shouldn't I? determinant A multiplied by determinant B, we can say determinant A times determinant B is going to be 3 times 6, or 18. So now we're going to find the product AB and check its determinant. All right, let's go into Simpy to save some time on this. So I'm going to go ahead and enter matrices A and B. Matrix A has in the first row 2, 0, 1, 1. Then the next row is 1, -1, 0, 1. The third row is 2, 3, 1, 0. And the fourth row is 1, 2, 3, 0. So here's matrix A, and then we'll enter matrix B. Oh, I made a typo somewhere in here. I forgot the comma here. Now let's check matrix B. Looks good. Okay, now let's do A times B. And there's our result, and it matches with my notes. And so now we want to do determinant A times B. So we can say determinant in parentheses A times B. And voila, we get 18. And we know that's a match for what we got doing the determinant of A times the determinant of B. And if you want to verify those calculations we did earlier, you can say determinant A and dt in parentheses B for determinant B. And we get the same 3 and 6 that we got by hand. All right, in the next video, we are going to take a look at the determinant of a scalar multiple of a matrix.